Integration of vector valued functions. So this is chapter number 5. Let's start with integration of vector valued function. Okay, so the acceleration of particle at any time t is given by the vector a is equal to dv dt is equal to 12 cos 2t I minus 8 sin 2t j plus 16t k. If the velocity v and displacement r are 0 at t0, find v and r at any time t. Okay, so let's find the velocity plus 16t and dt. So integrating both sides, we have v is equal to, so this will be integrated, so that is 12 sine 2t over 2 in I direction and plus 8 over 2 cos 2t j plus 16 over 2t square. Here is k direction and plus some constant vector. So the condition given is that v is 0 at t0. So when we put t0, what we get, 0 from here, 6 into 0 I plus this is 4 j, because cos 0 is 1, and this is 8 into 0 square k or plus vector c, but at that position the velocity is 0 vector. So what is c? C is in fact 4 minus 4 j. So the velocity at any time t become, putting this c, velocity at any time t is equal to, so we have, this is 6 sin 2t I and 4 plus 4 cos 2t and minus this, we will put this minus 4j, So that is 4nj and 8 t square k. So this is velocity at any time t. This is one answer. The second answer is we have, this is in fact dr dt, derivative of the displacement vector. So this implies that dr is equal to 6 sine 2t I plus 4 cos 2t minus 4j and 8t square k, and this whole dt. So we have to integrate to find the position vector, the displacement vector in fact. So that is r is equal to, integrating this one, that will give me minus cos, so minus 6 over 2 cos 2t I, and integrating this one, that will be 4 over 2 sine 2t and minus 4t j plus 8 over 3 t cube k and plus some constant vector. Let's take that constant vector bc1. So when we put r t0, the displacement is also 0. So r at 0 position is so this will give me minus 3 I, cos 0 is 1, and now from here sine 0 will give me 0, and that is 0, so 0j and 0k. And a constant vector, but this is 0, displacement vector is 0. So that means what is c? Oh, 0 vector. C1 vector is equal to 3i. So this is the ith component. This will be added into the ith component, this one. Okay, so let me write, if I succeed to write here the position vector, that is r is equal to, so this term and c will be put 3i, so they will be added 3 minus 3 cos 2t, that is I direction, and then plus 2 sine 2t and minus 4t z direction plus 8 by 3t cube, 8 over 3t cube in k direction. So I underline the things. This is the displacement at any time t, and this one is the velocity at any time t of the particle. So this is application of integration of vector valued function. We are given acceleration, so we integrated once, so to get the velocity vector, then put the initial condition that the velocity is 0 at t0, so that give me the velocity vector, this one. Okay, so this is the velocity, required velocity at any time t. This is the position vector or displacement vector at any time t. Okay, so we will okay, so for it we have to do some calculation over here. D by dt of a vector a cross dA and dt. So this is equal to dA dt cross dA dt, and then plus a d square a dt square. So we use product rule. First we have differentiate this one, leaving this one, and then we leaving this one we differentiate the second one. But we know that the cross product of this is 0 because same vector cross is 0. So what we left with? We left with the derivative of this expression is equal to a cross second derivative d square a dt square. So you see the integrand is a cross second derivative of a, so I will replace this by this value. So this implies the integral is the d by dt of a cross second, not second derivative, dA dt and whole dt. This is given over here. So this is first derivative, there is no square. Okay, so what we have, this dt will cancel with this one and this integral will cancel with the differential, so that give me a cross dA dt and plus some constant of integration. So that is constant. So this is the value of, we evaluated the integral a cross d square a dt square and dt. So this integral has this value. When we integrate it, we get this one, and the explanation are given over here. This is an important integral, and we will see in the next video that it is used in some planetary motion. So Newtonian mechanics, so we will use this in Newtonian mechanics in the next video. Okay, thank you.